Essay 57, A New Theorem of Geometry and General Relativity. The origin of this theorem can be understood by considering the simple clockwise rotation of a vector in a plane xy. It is obvious that the vector has been rotated with fixed axes. If the obvious is thought about, new discoveries are made. If the vector is kept unchanged and the axes y and x are rotated anti-clockwise, the end result is the same. The clockwise rotation of the vector with axes fixed is known as an active rotation, and the anti-clockwise rotation of the axes with a fixed vector is a passive rotation. The active rotation is equivalent to a passive rotation. It is exactly the same thing. This has been very well known for centuries and appears in every textbook. To start our train of thought, consider what is meant by an active rotation in terms of geometry. In the 1920s, the great mathematician Einstein Cartan developed the type of geometry that is used in the ECE Theory of unified physics. In this geometry, vectors and axes can both move, and they can move in any way. The movement of the axes is described by the word connection, and in Cartan's geometry, this becomes the spin connection. If the axes are fixed, there is no spin connection. An active rotation is therefore described by a geometry in which the spin connection is zero. The passive rotation is the rotation of axes with fixed vector. The idea of a fixed vector means that its derivative vanishes. The derivative of a constant is zero. So the rotation of the axes with fixed vector is described completely by the spin connection. The derivative is used so often in dynamics that it too needs to be thought about. The linear velocity, for example, is the time derivative of the position vector in 3 dimensions. The idea of the derivative can be extended to any number of dimensions n. It is then called the n derivative. In 4 dimensions, it is known as the 4 derivative. The use of 4 dimensions became centrally important with the advent of special relativity. The 4 dimensions became those of spacetime, and space was no longer independent of time. In the dimensions of spacetime, the 4 derivative is known as the ordinary derivative and is expressed by the mathematical methods introduced by Minkowski. The Minkowski spacetime is flat spacetime, which is described by a geometry in which there is no connection present. So movement in this flat spacetime is described by the partial 4 derivative of a vector, and a vector in Minkowski spacetime is known as a 4 vector. Motion in Minkowski spacetime is the motion of a vector with fixed 4-dimensional frame of reference. At this point, it is suddenly realized that this movement is equivalent to the movement of the frame of reference with fixed 4 vector, and that any type of motion of a vector in any number of dimensions is equivalent to the motion of the frame of reference, and any type of motion can be described by the spin connection, keeping the vector fixed. The derivative of the vector with a spin connection included is known as the covariant derivative of the vector. This means that the covariant derivative retains its tensorial format under the most general coordinate transformation. The ordinary 4 derivative does not retain its tensorial format in this way. The covariant derivative is a sum of 2 terms, the ordinary derivative and a spin connection term. The equivalence of active and passive rotations means that these 2 terms are equal. This is a new theorem of geometry and general relativity, valid in any mathematical space and any number of dimensions. A rotation of a vector in the plane xy is an example of the geometry of Cartan. The active rotation of the position vector with fixed axes is described completely by a derivative. For example, a time derivative to give the orbital linear velocity. The passive rotation of the axes with fixed vector is described completely by spin connection components. The passive rotation has never been considered in dynamics. When it is considered, any orbit in a plane can be described by components of the spin connection of Cartan. This means that orbital theory becomes a rigorously correct theory of general relativity to replace the failed Einstein theory. In the solar system, the planar orbits of planets and all objects around the Sun are described entirely by the spin connection. In other words, they are described by the movement of a frame of reference, an idea of general relativity. For any kind of rotational motion in a plane, the spin connections can be evaluated quite easily. These ideas can be extended to all types of orbits observable in astronomy, and a new cosmology has been forged. From the spin connection, we know the torsion and the field equations of the ECE theory of unified physics. It is important to think about the obvious.